Today we will be looking at lesson 2.09, I can see, can't you? And this is a pun because we're going to be talking about something called secant, or a secant line. So today's objective is, given 2 points on a function, I can calculate the average rate of change and describe its relation to the graph in 2 out of 2 problems. So we've talked about rates of change a little bit. We may or may not be familiar with what averages are. We're going to string all those words together today and make kind of a new vocabulary phrase, an average rate of change. We're going to talk about what that means. So first, what does the word average mean in general? When we use the word average, when we're talking just, common, talking to our friends, what do we mean when we say something is average? Well, we might mean it's typical or common. We might think of it as middle of the road. What else might average mean? It just kind of means most of the people are like this, or most are similar, right? Average means that, if you talk to anybody in general, they might have this average characteristic. So when we apply this word to math, maybe you've heard this word in math before, it's a way of finding the middle of a set of numbers. So it's kind of the same idea as we use it in general. It's kind of the middle, the typical. It's a number that we will use to represent a set. So the way we find the average is we add the numbers and we divide that by a count of the numbers. And that will give us a number that's somewhere right in the middle of all the numbers. So let's look at a few examples of how to calculate an average. So we're going to add the numbers first. We do that on top. And then we count the numbers. We have 1, 2, 3, 4. So I'm going to divide it by 4. Now I'll put all those in my calculator. 16 plus 12 plus 9 plus 3 is 40. Divided by 4, we'll get 10 is our average. And if you look at these numbers, that kind of makes sense. 10 would fall right here in the middle of these two. So that makes sense. How about the second one? How would we set this up? Well, we're going to add the numbers, 2 plus 6 plus 0 plus negative 1 plus 3. And then we're going to count the numbers, 1, 2, 3, 4, 5. There are 5 here. Now notice 0 is a valid number. If 0 appears in our set, we do count it. Even though when we add 0, it doesn't change the sum, it's still a valid number. It's still a valid part of our set, so we do count it. So this is 1, 2, 3, 4, 5. We do not remove the 0. 2 plus 6 is 8, plus 0 is still 8, minus 1 is 7, plus 3 is 10. This will be 10 over 5, which equals 2. Pause the video on this last one and see if you can calculate the average on this last set, and see if you get the same thing I do. So we're going to add the numbers on top, and we're going to divide by the count, 1, 2, 3, 4. I need my calculator for this one again. 18 plus 27 plus 36 plus 45. I get 126. That'll be divided by 4, which is 31.5. Notice our average can have decimals. That is totally possible. It doesn't always have to be an integer. So in this lesson today, we're talking about average rate of change, right? So it makes sense that maybe we're going to be talking about rates of change. We've talked about how numbers are changing, but now we're going to be averaging them. We're going to average a whole set of them. So let's look at an example from real estate. Talk about values of houses. Kwan's parents bought a home for $50,000 in 2007, just as real estate values in the area started to rise quickly. Each year, their house was worth more until they sold the home in 2017 for $310,000. So they made a whole bunch of money just by buying a house. Looks like they made about $260,000 over that time period. Now we could model this in a table like this. Let me scroll a little bit. There we go. And if we want to predict home prices in the area, we could model it with an equation, right? That could help us figure out how much homes might be worth in 10 years from now or 15 years from now. But it makes a difference whether this is linear or exponential, right? We have a value at the beginning, a value at end, and we'd have to figure out what these numbers are in between to figure out what the next numbers would be. So we have a couple of different options. We could do linear. We talked about how to do this. We'd be adding the same value at each step, right? We would do that 10 times. So we'd end up solving an equation that looked like this. 50 plus 10r equals 310, right? Because we started with 50, we add r 10 times, we get to 310. And we have solved that before. Or we could also look at geometric. We could think, well, maybe we'd be multiplying by r at each step instead of adding. In that case, we'd set up this equation to be 50 times r times r times r 10 times, right? 50 times r to the 10th, that's how we write r times r 10 times, equals 310. So if we wanted to set up a linear equation, find the common difference, we'd solve that one. If we wanted to set up an exponential equation, we'd solve this one and find the common ratio. We have already done this before, so I don't want to focus on that in this lesson. So I've already done that for you. You can see if we add 26 each time, 26, 26 again, 26, we go from 50 to 76 to 102 all the way up to 310. So this is our common difference. Over 10 iterations we get from 50 to 310. Notice I've put this in thousands of dollars, mostly just because I don't want to write all those zeros. So this is $50,000, $76,000, all the way up to $310,000. And the question I want to ask here is, what is our equation? Can we model our linear equation for this pattern? Well, we know that linear equations follow the form mx plus b. M is our common difference, and b is our value at 0. So this will be f of x equals 26x plus 50. So that's our linear modeling of this. Now how about our exponential modeling? Our common ratio now is 1.2. That's what we're going to multiply by each time, multiply by 1.2. So what would our equation be in this case? Oh, let's not do f of x, let's maybe do g of x. This is going to take the form a times b to the x because it's exponential. We know that our geometric sequences are exponential. A is our value at 0. B is our common ratio. So this will be g of x equals 50 times 1.2 to the x. So those are our two models. Notice that we started with the same value. They both started with $50,000. They both ended with the same value, $310. But the numbers in between are different. We'd expect that in a linear equation versus an exponential equation. They're growing at different rates. So whenever we're comparing linear and exponential equations, it's always a great idea to put them on a graph, see what they look like together. Putting things on a graph really helps us visualize and be very intuitive for our understanding. If you have a different graphing calculator than Desmos, that's totally cool. You can use that one too. Desmos is just available online, very handy. So I put these equations into Desmos, and I zoomed out a little bit, changed the scale a little bit, and I was able to get this picture right here. Here's our linear model. Here is our exponential model. What do we see here? What do we notice? Well, maybe you might notice that they intersect at 2 points. There and there. You might notice that we have one straight line and one curved line. You might notice that g of x starts out slow but grows faster as it goes on. So it starts slow and it gets faster. Whereas if we look at f of x, that's not changing its rate. It's actually going the same the whole time. So that's the same rate the whole time. So I'm going to introduce a vocabulary term here. A secant line is a straight line that passes through 2 points of a curve. So this is an example of a secant line. F of x is a secant line for g of x at these 2 points. We've talked about several examples of these in yesterday's lesson and assignment. So it's common enough and useful enough that we actually gave it its own name. This is a secant line, a straight line that passes through 2 points of a curve. And just store that in the back of your mind for a second. We'll get back to it in just a second. So since we're looking at average rate of change today, let's dig a little bit deeper into what we mean by rate of change on these functions. For our linear model, we're going to find the difference between each year and then average all the differences. That's what we mean by average rate of change, right? Here's the rate between these two. Here's the rate between these two. We can calculate that each time. And then if we want the average of them, we can add them up and divide by the count. So 76 minus 50 is 26. Our next one would be, maybe I want to use blue. Let's try blue. Our next one would be 102 minus 76, which I believe is 26. And then we have 128 minus 102. That looks like 26. Do you notice a pattern forming? Let's see, 154 minus 128. That is 26. Oh, these are all 26, right? We don't need to calculate these every time. We know that that's actually how we defined this equation in the first place. It's linear. It's arithmetic. We added 26 each time, so we know that the difference is going to be 26. That's exactly what the term common difference means. It means the difference is the same every time. 26 in this case. So to find the average of them, here we go. We're going to add all of them together. There are 10 of them, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we divide by the count, which was 10. Well, adding a number 10 times is the same thing as multiplying by 10, right? So this is going to be 26 times 10 divided by 10, which is 260 over 10, which gives us 26. Our average rate of change is 26. Now, let's think about that conceptually. An average is the middle of a set of numbers. If all the numbers are exactly the same, well, of course the middle is going to be that number. So we just went through a whole bunch of arithmetic just to figure out that, yes, the middle of a set of all 26s is still going to be 26. But when we look at the exponential function, it's going to be less trivial. So let's check that one out. So we're going to do the same process here. We're looking at the difference between each step, but now it's going to be changing, right? Because it's exponential. So we have 60 minus 50 is 10. 72 minus 60 will be 12. 86 minus 72 is 14. We might see a pattern here, but let's be really careful because we know exponentials grow. So 104 minus 86 is 18. 124 minus 104 is 20. 149 minus 124 is 25. It looks like the pattern is changing. It's growing. 180 minus 149 is 31. 215 minus 180 is 35. 258 minus 215, that looks like 43. And our last one, 310 minus 258, is 52. All right, so we want to know what the average rate of change is. This is our rate of change between each of these numbers. So we want to add them all and divide by the count. So here we go, 10 plus 12 plus 14 plus 18 plus 20 plus 25 plus 31 plus 35. 43, and our last number is 52, and our count is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, don't want to cross it out. There we go, divide by 10. Okay, let me put all that in my calculator. 10, 12, 14, 18, 20, 25, 31, 35, 43, 52. I get 260 on the top over 10, and that will equal 26. So our average rate of change here is 26. Now let's compare our linear and our exponential here. We started at 0, 50, we went to 10, 310. In our linear model, our average rate of change was 26. In our exponential model, our average between those 2 points was still 26. What? They're the same? They are, in fact, the same. For any function, the average rate of change between 2 points is equal to the slope of the secant line between them. Whoa! So let's just put all the vocabulary terms in one sentence, shall we? Let's break this apart for a second. The average rate of change, that's what we just did, right? The average of all these differences between any 2 points, the average of those is going to equal the slope of this line that's connecting the 2 points. Remember, the secant line is a straight line that runs through 2 points of a curve. So that means that this line, the slope of this line is going to be the average rate of change of this curve. And that's going to be true of any 2 points on the curve and the line that runs between them. So here's a conceptual question for you. If we were looking at the straight line instead of the curve, we were looking at the linear equation, what would the average rate of change be between any 2 points? These 2 points, for instance. what would the average rate of change be? Well, in this case, it's 26, right? We know that the slope is 26 here. But in general, for any linear equation, it's going to be equal to the slope. The average rate of change for a linear equation is always equal to the slope. So basically, we're asking, how do we find the slope between 2 points? If we can just find the slope between 2 points, then we save us all that work of calculating all the difference and then dividing and calculating that average. That took a long time. So let's think about it. If we have a graph, we know how to find the slope, right? We just know that this is rise over run. And by the way, you may see this notation. This is a delta. It's a Greek letter. And this means change. When you see a delta in mathematics, it means the change. So this just says the change in y over the change in x. So if we have a graph, we can do the rise over the run. We can say we start here and we go up 2, and we go over 1, 2, 3, 4. So then our rise over our run will be 2 over 4, which is 1/2. But say we don't have a graph. I'm going to take all of this off for a second. Say we don't have a graph. Say they only gave us these 2 points. How do we calculate it now? Well, we could draw a graph. But is there a way we could do it with just algebra so we don't have to draw a graph and we don't have to get Desmos out? Well, let's take a look here. So our y value at this point, our y value here is 3. And our y value here at this point is 1. So you can expect that the length of the line between them is just going to be the difference. It's going to be 3 minus 1. And that equals 2. Similarly, over here, the x value is 6. So this is a 6. And the x value at this point is 2. So the difference between them will be 6 minus 2, which is 4. So this is our rise, this is our run. The difference between the y's was our rise. The difference between the x's was our run. We put the rise over the run. So this was 3 minus 1 over 6 minus 2. We call slope m often. So this will be 3 minus 1 is 2, 6 minus 2 is 4, and once again we get 1/2. We can generalize this formula like this. M equals y2 minus y1 over x2 minus x1. Now what do these subscripts mean? This little 2, this little 1, what does that even mean? It means that we have numbered these points. This is point number 1, this one is point number 2. And so if we were to write this as x and y, this would be x subscript 1 and y subscript 1. Up here, this one would be x subscript 2 and y subscript 2. So then when we say y2, that's going to be this 3 value right here. y1 will be the y value from our first point, from our point number 1, so that will be 1. The main trick to getting slope correct, the trickiest part, is to make sure you get these in the correct order. So I usually go through extra steps just to make sure that I got them in the correct order. Let's look at an example. Let's go back to our real estate example. And we want to find the slope between those years we talked about. At 0-50, at the beginning they had $50,000 home. And at year 10, they had a $310,000 home. Let's find the slope between them. Now, first off, we already know what it is, right? Because we've been talking about the slope of this line the whole time. What's the slope of that straight line? It's 26. So if we go through this whole process, we're going to expect it to be 26. That's what we're looking to find. let's prove to ourselves that it works. So I'm going to write my equation. Slope equals y2 minus y1 over x2 minus x1. You can see that listed up here as well. And to make sure I get these in the right order, I like to be very organized about it. This is how I do it. So I draw a little table like this. And I say this is x and y, and this is points 1 and 2. And then I just write the points. So point 1 is 0, 50. Point 2 is 10, 310. So y2, I'm going to go to y and 2 and go the number between them to find y2. That's 310. y2 minus y1. y1 is 50. On the bottom we have x2. x2 is 10 minus x1, which is 0. 310 minus 50 is 260. 10 minus 0 is 10. And overall, we do get 26. It matched. That is excellent news. So let's look at a couple more examples of how to calculate slope between 2 points. This table shows a car's speed as it accelerates. And our first question here is, what is the average rate of change between seconds 1 and 4? Okay, so we have time in seconds and speed over here. And my first thing is I want to mark the points that we are interested in here, 1 and 4. So I'm just going to draw a box around them. There's second 1, and then there's second 4. We want to know the average rate of change. I'm going to name this point 1 and this point 2. You can actually name these in any order. If you wanted to call this one 2 and this one 1, it doesn't matter. That's fine. The names are arbitrary. And then our input is x, our output is y. So now I can do y2 minus y1 over x2 minus x1. y2 is 28. y1 is 7. x2 is 4. x1 is 1. 28 minus 7 is 21. 4 minus 1 is 3. And 21 divided by 3 is 7. But hold on just a second. Let's step back. Look at this pattern. 0, 7, 14, 21. Do you recognize what pattern's happening here? What would we call this? We're adding 7 each time, right? This is an arithmetic sequence, linear equation. So we already knew that the slope was 7. We already knew that the common difference was 7. So we totally expected this to be 7 already. It's great that we did the calculation and it came out as 7. But we also know that because it's linear, we didn't have to do that whole calculation. We know that if we know the slope, we know the average rate of change because they're the same. So let's ask this second one. What is the average rate of change between seconds 4 and 5? Well, we could calculate it again, but we already know it's 7 because between any 2 points it's going to be the same as the slope. It will always be 7 for a linear equation. Now the same is not true for an exponential equation. This table shows the spread of a wildfire over several days. On day 0 it started at 50 acres. It was up to 190 on day 1, 722. So this is jumping huge amounts. This definitely looks to not be linear. We would guess this is possibly exponential. So once again, we're asking, what's the average rate of change between days 1 and 3? So I'll just do the same process here. I'm going to draw my box around day 1 and my box around day 3. This is my x and my y, point 1 and point 2. So I'm doing y2 minus y1. y2 is 2744. y1 is 190. x2 is 3. x1 is 1. Now I need my calculator for this. 2744 minus 190. I get 2554 for our numerator and 2 in the denominator. Overall, that is 1277. 1277. Now I'm going to change my color for this one because we do actually expect it to be different when we go between days 3 and 5. So once again, I'm going to draw my box around the points we have interest in. There's 3, and there's 5. And just to demonstrate that you can do these in any order, I'm going to leave this one as number 2 and do this one as number 1 this time. It should work out the same way. So we get slope is y2, that's going to be 2744, minus y1, which is now 39618, over x2, which is 3, minus x1, which is 5. So on the top we get 2744 minus 39618. I get negative 36874. And on the bottom we have 3 minus 5, which is negative 2. Let's see, those negatives are going to cancel. And overall I get 18,437. So this is to be expected for an exponential equation. You can see it's getting bigger over time. The rate of change is changing. It's getting bigger the more days we have. And let's think about what these terms actually mean. Acres per day. This is 1,277 acres burned in this fire per day between days 1 and 3. But by the time we get to days 3 and 5, it's already up to 18,500 acres per day. We've gone from like 1,000 acre per day to 18,500 acres per day. So this fire is growing at an incredible rate, huge rate. And we can figure that out with the rate of change, the average rate of change between the 2 points. So that covers everything for today. Given 2 points on a function, I can calculate the average rate of change and describe its relation to the graph. Remember, the average rate of change is the slope between the 2 points, and its relation is the slope of the secant line between those 2 points.